This is section 8.5 on alternating series. So it alternates back and forth between positive and negative terms. It says let a sub n be positive terms, the alternating series, the sum as n goes from 1 to infinity of negative 1 to the n times, that should say a sub n, not a to the n. So the alternating series, whether the first term is a negative number or the first term is a positive number, it doesn't matter. So the alternating series will converge only if the following two conditions are met. We have to meet both of these conditions. The first is the limit as n goes to infinity of just the sequence part without the alternating part. So you can disregard the negative 1 to the n. Needs to go to 0. And also every term needs to be less than or equal to the previous term. So the terms need to be going down. Again, disregarding the negative signs. We're only concerned about the term value without the positive or negative. So the terms need to be decreasing in value or equal to the previous term. That's okay. And also the limit as n approaches infinity of a sub n needs to go to 0. So example 1 asks us to determine the convergence or divergence of the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 1 over n squared. This tells us that we have an alternating series. It also tells us if I plug in 1, my first term is positive. So because we have an alternating series, we're going to check these two things. We're going to check to see if the limit as n approaches infinity does go to 0, and if I have decreasing values in my terms. So the limit as n goes to infinity of a sub n. The a sub n is just this part without the alternating part. So 1 over n squared. If I plug in infinity, I get 1 over an infinitely big number, which does go to 0. And there's a couple different ways you can take care of the decreasing terms. Really, the official way is to look at the derivative. So f of x is 1 over n squared, which is n to the negative second. So the derivative is negative 2n to the negative third, negative 2 over n cubed. And remember, n starts at 1 and goes to 2, 3, 4, all the way up to infinity. So the bottom's going to be positive here, which means this is always negative. And if the derivative's negative, that means that the terms are going down. A more efficient way of looking at it sometimes, this one's not bad because the derivative here is pretty easy to get, would just be to start plugging some stuff in and seeing what happens to my terms. So if I plug in 1, I've got 1 over 1. And then my next term, if I plug in 2, is 1 over 4. Plug in 3 is 1 over 9, 1 over 16, 1 over 25. Pretty clearly, the bottom's continuing to get bigger and the top's staying at 1. So my terms are indeed decreasing. Again, without the positive or negative, we're not worried about that. Therefore, this one converges. Example 2, determine the convergence or divergence of this guy here, n over negative 3 to the n minus 1. Notice if I plug in 1, I get negative 3 to the 0, which is positive. Plug in 2, I get negative 3 to the first, which is negative. Plug in 3, gives me positive, and so on. So it's alternating. We want to check the two conditions of the alternating. We can evaluate the limit as n goes to infinity. We're going to take out the alternating part, which is the negative here. Really, this is like negative 1 to the n minus 1 times 3 to the n minus 1. So I'm going to take out the alternating part. So we've got n over 3 to the n minus 1. Plug in infinity, I've got an infinitely big number on the top and an infinitely big number on the bottom. So we use L'Hopital's rule. 3 to the n minus 1 has a derivative of 3 to the n minus 1 times ln of 3. I've got 1 on top and an infinitely big number on the bottom. It does go to 0. And then we want to check the terms. If I plug in 1, I get 1 over 3 to the 0. Plug in 2. Gives me 2 over 3 to the first. Plug in 3. 3 over 3 to the second. Plug in 4. 4 over 3 to the third. 1, 2/3 is less than that. 3/9 is less than that. 4 over 27 is even less than that. Notice on the top I'm just adding 1 each time, whereas on the bottom I'm multiplying times 3. The denominator is going to continue to grow bigger, faster than the numerator. My terms are indeed decreasing. This one converges as well. Example 3. We've got an alternating series, n minus 2 over 3 to the n. Evaluate the limit as n goes to infinity of the sequence without the alternating part. You can either use L'Hopital's rule or remember the rule for polynomial divided by a polynomial. Degrees are both 1, so we divide the leading coefficients. 1 divided by 3. 1/3. That is not 0, therefore we can stop right there and say diverges. It does have to meet both conditions. Example 4. Determine the convergence or divergence of this. So I've got 2, 1, 2, 1/2, 2/3, minus 1/3, 2/4. Notice these are getting smaller as it goes down. It appears as though the limit as n approaches infinity is going to go to 0. Looks like if we do the pattern here, it'd be like plus 2/5 minus 1/5 plus 2 over 6 minus 1 over 6. Notice these are continuing to get smaller. They do get closer and closer to 0. We also want to check to see if my terms are decreasing. 2, 1, 1, it stays the same, that's okay. 1/2, it went down. Now it went up to 2/3. Goes down to 1/3, goes up to 1/2. Diverges. If you need to give a reason, the reason would be because the terms are not all decreasing. The reason why that's important is if I start with 2, I take off 1, I add 1 back. I take off 1/2, but then I add back more than what I just previously took off. I take off 1/3, but then I add back 1/2. So kind of if we group these together, like these two here, whatever this sum is, I'm adding something on here. And then here I add something more on. And here I would add more on. So if I'm continuing to add things on, the sum's not going to go to one specific number. It's going to get infinitely big. So this says the sum of a sequence is called absolutely convergent if without the alternating part. So if I take out the -1 to an n, or -1 to the n, if that also converges, that is called absolutely convergent. If it converges both if it alternates and if it doesn't alternate, it is an absolutely convergent series. If the alternating one converges, but if I take out the alternating part and it no longer converges, that is called conditionally convergent. So this one here wants to know, is this an absolutely convergent series? Is it conditionally convergent, or does it diverge? So let's check the alternating part first. The limit as n goes to infinity of 1 over n is indeed 0. And if I plug in terms, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, notice my terms are indeed decreasing. So this is a convergent series. We need to figure out, is it absolutely convergent or is it conditionally convergent? And to do that, you consider the series without the alternating part. So if I take out the alternating part, I've got this. That is a p series, where p is 1. This diverges. So it converges if it alternates, it diverges if it does not alternate, therefore it is conditionally convergent. I want you to try these two. Pause the video, see if you can make the correct decision on these two, if each of these is absolutely convergent, conditionally convergent, or if they diverge. Once you think you have it, start the video back up. This first one here, we could try to find the limit as n goes to infinity of a sub n, but I've got an absolute value in there, or not an absolute value, a factorial in there. I'm not going to mess with that. Let's see if we can prove that it diverges with the second part of it. And then if not, maybe we'll come back and revisit this. So if I plug in 1, I get 1 over 2. Plugging in 2 gives me 2 over 4. Plugging in 3 gives me 3 factorial. 3 times 2, that's 6 over 8. Plugging in 4 gives me 24 over 2 to the 4th, 16. Notice 1/2, 1/2. Now it's getting bigger. 3/4. Something more than 1. Was that 3/2? So my terms are not decreasing, therefore this diverges. The second one, very similar to the one that we did in example 5. The limit as n approaches infinity of 1 over root n is indeed 0. And 1 over 1, 1 over root 2, 1 over root 3, 1 over root 4. These terms are indeed decreasing. So this series converges. 1 over root n is a p series. P is less than 1, therefore this one diverges. Therefore this is conditionally convergent. Notice all p series, so 1 over n, if the p value is more than 1, it absolutely converges, whether it's alternating or not. If it's 1 over n to the first, or 1 over n to the 1/2, or 1 over n to the 1/7, as long as this is a positive number. If it's negative, it moves up to the top, so that changes it. But if this is a positive number, even if it's less than 1, if it alternates, it is still going to converge. It's going to meet those two criteria. So if it doesn't alternate, it diverges if p is less than 1. But as long as p is positive, the alternating part will converge. A couple other examples. This one asks us to consider this series. The sum as n goes from 1 to infinity of sine n over n squared. If I plug in 1, I get sine of 1 divided by n squared. Sine of 1 is a positive number. Next number I would plug in is 2, so sine 2, I get a positive number, and then sine 3 I'm getting a positive number. Sine 4, now I'm getting a negative number. So some of these terms that are positive, some of them are negative. Some positive, some negatives, but they don't necessarily even alternate back and forth between consecutive ones. But this is a good thing to know. If we take the absolute value of a function and this series converges, and the series, whether it was pluses or minuses in there, is also going to converge. So basically, if everything's a plus and we know that converges, I can change some of those to minuses and it's still going to converge. So going back to this example, if I take the absolute value of this, now they're all positive. So I have some numbers, I've got numbers, all those numbers are less than 1 over n squared. This is a p series. B is 2. Therefore, it converges. So if they're all positive and it converges, even if some of them are negative, it still converges. And last example here, it looks kind of funky. The sum as n goes from 1 to infinity of sine of n pi over 2 times 1 over the cube root of n. If we plug stuff into this part here, if I plug in 1, I get sine of pi over 2. Sine of pi over 2 is 1. If I plug in 2, I get sine of 2 pi over 2, sine of pi. So my second term is 0. If I plug in 3, I get sine of 3 pi over 2. That's negative 1, and then I'm getting sine of 2 pi. That's 0. Sine of 5 pi over 2 is 1. So that's, if I listed out all the terms, notice my first term is 1 over cube root of 1. And then the next term is 0. Then if I plug in 3, I'm getting minus 1 over the cube root of 3. 0 plus 1 over the cube root of 5. Notice this alternates. This is another way of showing that it alternates. If it's got sine of n pi over 2 or cosine of n pi over 2, something like that in there, it's going to be an alternating series. So this here, this is just showing, this is another way to make it alternate. They do it this way if it skips over some terms, like we don't have the 1 over cube root of 2 in there. But really all we need to consider is the two rules. Because we know it alternates, we want to check the limit as n approaches infinity and show that the terms do decrease. Also, you could recognize this is a p-series. An alternating p-series, as long as p is positive, will converge. So this converges. Because if I take out the negatives, it no longer converges. It would be a conditional convergence if it asked that. That is section 8.5 on alternating series.